When we look at a mixture that's at equilibrium, there's two types of processes that can alter the equilibrium concentration. And those two types of processes could be categorized as the following. Changes that do not affect the equilibrium constant. So they're not changing the numeric value, or there are processes that do affect the equilibrium constant. Okay, so as a reminder, the only variable that we talked about so far that can change the equilibrium constant, temperature. Okay, because every time we calculate an equilibrium constant, that's at a certain temperature that value works. If we go above or below the temperature, we need a new equilibrium value. Okay, so let's talk about the first process. Changes that do not affect the equilibrium constant. What possible condition changes can change the composition at equilibrium? Well, there's three. We could change the concentration. We could change the pressure. Or we could change the volume. So doing one of these changes, the concentration, the pressure, or the volume, that's going to affect that will affect the equilibrium concentration, but it will not change the value of the constant. Okay. Now, what does a catalyst do to an equilibrium mixture? Does that change things? No. So why does it not change? Keep in mind that catalysts do nothing to the energy balance. It only makes the reaction go faster by lowering the activation energy. So the catalysts do not change or add to the energy balance. It can only make the reaction go faster by lowering the activation energy. Okay, now the general statement about the effect experimental changes on an equilibrium mixture is the Châtelier's principle. Now, in each general chemistry course, there's usually a really big idea that is like the key for the course. So, like for Gen Chem 1, the big idea in that course was the kinetic molecular theory. Because with KM theory, that explained how gases and liquids and solids behave. For the second half of the course, it's this, Le Châtelier's principle. So what does Le Châtelier's principle say? It says this: if stress is applied to a reaction mixture, at equilibrium, the net reaction occurs in the direction to relieve that stress. All right, so let me say this again. Le Châtelier's principle says this: if you're applying some sort of stressor onto a chemical reaction that's at equilibrium, the reaction is going to find a way to alleviate that stress. Okay, just like people, when you get stressed out, you have something, you do something that allows you to alleviate that stress, albeit temporarily, but you do something to alleviate that stress. Chemical reactions behave the same way as people do. When a chemical reaction is stressed, they find a way to alleviate that stress. And so that's what we're going to be talking about. So by changing the concentration or changing the pressure or changing the volume, when we apply some sort of stressor, by changing the concentration or by changing the pressure or changing the volume. The chemical reaction finds a way to relieve that stress that we just put on that chemical reaction. So what we're going to do the rest of the time today, or on this video, is to find way, look at situations, and then see does a chemical reaction relieve stress that's placed on it. Okay, so what we're looking at now is how does changing the concentration affect the equilibrium? So to start us off, let's take a look at a reaction, and here it is. N2 plus 3H2 is in equilibrium with 2 moles of NH3. And this is all gaseous. All right, so here we've got a graph. And this is kind of like another reaction coordinate diagram. So what we're looking at, initially we're at equilibrium. So let's say reaction started, we started with no concentration of NH3. We have H2 and N2. If they react, we get to equilibrium. So this is where we're at. So the pink area or the peach area, we're at equilibrium right now. So the way that we're saying that is the reaction quotient QC is equal to KC. We're there. Okay. And so here's our concentration of H2. It's at 3 molar. Concentration of NH3 is at 2 molar. N2, 1 molar. All right. So what we're saying now, at the end of this time, what if we change the concentration of N2 and add more N2? So then we change the concentration from being half a mole, we'll make it 1.5 moles. So by changing that concentration, how does it change the others? Well, looking at H2, okay, once we start adding that N2, the concentration of H2 drops, while the concentration of N2 also goes up, but then it also starts to drop and level out. Concentration of NH3 actually increases, and then it pretty much equilibrates out till you get to a new equilibrium. All right, so how did this reaction relieve that stress of adding N2? So by adding N2, you had to use up more H2 over here in order to make more NH3. So if the stressor here was N2 because we added more, what this ended up doing was shifting this reaction over to the right to make more NH3 than previously before, because our stressor here was the N2. And to alleviate that stress, the N2 reacted with the H2 to make more product. So that's kind of how this reaction relieved that stress. It made more product. We increased the concentration of a reactant. It, in turn, made us make more product. So if we were to write the chemical equation again, you have N2 plus 3H2 is in equilibrium with 2 moles of NH3. The equilibrium expression would look something like this. Kc would be equal to the concentration of NH3 squared divided by the product of N2 times concentration of H2 cubed. Okay, oops. I'm writing the numbers backwards. So that was H2 cubed. All right. So right after that, so here's our question. Even I just walked through I just talked us through it. So right after adding that species, which was N2, right after adding that species, what could we say about the reaction quotient compared to Kc? Well, at that point, the reaction quotient was actually less than the equilibrium constant. And that's how we knew we weren't at equilibrium anymore. So what subsequent changes do you see for each substance? We saw that the concentration of N2, even though initially went up, concentration of N2 actually went down a little bit. Okay. So again, looking at this graph, it went up, but then it went down a little bit because you still had the H2 reacting. So we saw that the concentration of N2 did initially go up, but it definitely went down and leveled off. Okay, H2 definitely went up. And then NH3 also went up. Now, according to the equation, if the ratio is 1N2 to 3H2, that means that it went up 3 times for H2 and 2 times for NH3. Okay, so how do these changes affect the reaction quotient? We saw that QC increases as it approached KC. All right, so let's try another case. We're going to draw a figure like we did above, but this time we're going to show a major increase in H2. All right, so what I'm going to do is let's go back to this drawing right here, our graph. Okay, we're going to expand this a little bit. Okay, so we're going to add more H2. So what should happen? So let me get a pink marker here. So what I'm going to do is increase H2. Okay. Now, if I'm adding stressor to the system, this time I'm adding H2, same things that's going to happen. If the stressor is on the left-hand side, it's going to alleviate it by making more product. So ideally, what should happen is that even though the concentration of H2 goes up, eventually it's going to go down a little bit and level off. Okay. We should see that the concentration of NH3 is going to increase until it levels off again. What we're going to see with N2 is that concentration is going to go down. So let me get a darker color here. So what we're going to see is that because we're using up H2 to make more product, the concentration of N2 is actually going to go down until it levels off again. So at this point, this is your new equilibrium, where QC is equal to KC. And so to answer that question, that's what this would look like at equilibrium. If we were to increase the concentration of H2, you increase it initially, but it's got to decrease because you're using up more N2 to make more product. What if we change the volume and the pressure this time? So let's look at the same reaction before. So you still have N2 plus 3H2 yields 2NH3. Everything's in equilibrium with each other. The Kc for this reaction is 0.291 at 700K. Now we looked at the last section, what happens if you add more product, and we change the concentration. Let's change the concentration by changing pressure and volume. Okay. Now, if the equilibrium concentrations are N2 is equal to 0.5 molar, H2 is 3 molar, and NH3 is 1.98 molar, what is QC for this reaction? So if we set this up and solve for QC, we know the concentration of this expression would be concentration of NH3 squared divided by the product of the concentration of N2 times the concentration of H2 cubed. Okay, and if we put our numbers in, the concentration of NH3 is 1.98 squared divided by 0.5 times H2 3 molar square cubed. Okay, so if I type these out real quick, 1.98 squared, okay, 0.5 times 3 cubed, okay, and then divide them, that should give us 0.2904. So that's our value. Now Kc for this reaction was 0.291. So we're really close. With these concentrations, QC is definitely lower than Kc, but it's extremely close. We're almost there. It's really close. It's really close to equilibrium. Okay. Now, what happens if we increase the pressure by halving the volume? And then what happens to the pressure? Well, remember that the ideal gas law says this: PV equals nRT. Okay. So, looking at Boyle's law, the pressure is going to be correspond, or it's going to have an inverse relationship with the volume. So if the pressure is going up, volume's got to go down. And vice versa. Volume goes down, pressure goes up. So if the volume is cut in half, then the pressure doubles. Okay. Now, what if we triple the pressure? Okay. So if we triple the pressure, so let's say it's 3P now, this would be corresponding to something like 1 over 3 the volume. So it's going to be a third of the volume. So the response, by tripling the pressure, which means the volume's cut, we triple the pressure, which means the volume's cut to a third, it shifts the reaction to make more product. Okay. And if we do the math with this, using our new volumes, what are the new concentrations? So those would be, let me put these in. So the concentration of N2 would be 1.5. The concentration of H2 would be 9 molar. And then the concentration of NH3 would be 5.94. If we solve for QC, using our expression before, that would be 5.94 squared divided by the product of 1.5 times 9 cubed. So that value should be 0.0322, which that value for equilibrium was again 0.291. So that means that QC is definitely way less than KC. Okay, and so where's the reaction at now? It's now left of equilibrium. So it's definitely it's favoring the reactants. Okay, so another way, and so since it's left of the equilibrium, it's favoring reactants. That means the reaction's got to move in order to get to K equilibrium. It's got to move to the right, so it's going to make some more product. So another way to change the pressure is to add a non-reacting gas to the mixture. What will this do to an established equilibrium? Nothing. So adding a non-reacting gas to the mixture does nothing. So there's no change in the partial pressure. And because there's no change in the partial pressure, it's inert. So it doesn't react. All it's doing, all that gas, that non-reacting gas is doing, is just increasing the overall pressure. So the examples we've looked at so far, changing the concentration, changing the pressure, and changing the volume, all of those will not change the overall equilibrium constant. Okay, so now let's take a look at the one thing that does change the equilibrium constant: temperature. If we make changes in temperature, we make changes in the equilibrium constant. Okay, and a simple view is this: if energy is involved, changes in temperature will cause a change in the effect being considered. Okay, so if we go back to the reaction we've been looking at, N2 plus 3H2 yields N2NH3. Here's our reaction. On the left, on the y-axis, we're looking at the equilibrium constant. X-axis, we're looking at temperature. Okay, and Kc is plotted on a logarithmic scale, so that way it's a lot easier to see this. But we can definitely see that Kc is increasing or decreasing by a factor of 10 to the 11th on raising a temperature from 3 to 1,000. Okay, and so we can measure that if we measure the slope we can see that Kc is definitely decreasing. Now, the change in temperature is large, but the change in K is enormous at 100 billion. Okay. Now, to show why K is so sensitive to the temperature, we have to go back to a familiar graph. And I know this is like the fifth time that I've taken this graph out, but and remember, at a lower temperature, you're going to have less of a fraction of molecules that are ready to that will be colliding at the right energy. And if you increase the temperature, you do increase the fraction of the molecules that collide with the right amount of energy. So if you change the temperature, you change the fraction of molecules with high enough energy to react. Okay. Now, the most critical parameter that determines the effect of temperature on equilibrium is actually our friend from Gen Chem 1, the change in enthalpy of the reaction. How is that so? Well, it turns out that the equilibrium constant for an exothermic reaction, okay, and remember, exothermic means that the enthalpy is going to be negative, decreases as the temperature increases. Okay, and it turns out that the Kc for an endothermic reaction, so we're talking about a positive change in enthalpy now, this increases as the temperature increases. Okay, all right. So let's take a look at two examples of thermodynamic equations. So here's our first reaction. Let's take a look at our same one that we keep looking at. So N2 plus 3 moles of H2 is in equilibrium with 2 moles of NH3. Okay, now everything's gaseous. And the enthalpy for this reaction is negative 92.2 kilojoules. Okay. And so if I was to, this is what a thermodynamic equilibrium equation looks like. Another way to write this is to put since this is going to be a negative value, we know this is going to be an exothermic reaction, so that means the energy is part of the products. So we could also write it this way, where that value is directly into the equation on the product side. So it will be 2 moles of NH3 plus 92.2 kilojoules. Okay. Another way to do this, another equation would be if we took N2O4, and that's in equilibrium with 2 moles of NO2. Okay. The enthalpy for this reaction would be 55.3 kilojoules. And so since this is endothermic, that value would be on the left-hand side. So we would write it as our reactant. So N2O4 plus 55.3 kilojoules. That's an equilibrium with 2 moles of NO2. All right, so we talked about changing concentration, we talked about changing pressure and volume, and we talked about changing the temperature and how this all affects equilibrium and using Le Chatelier's principle to tell that story. The last thing we want to do in connection with Le Chatelier's principle is figure out how do catalysts not do anything. But more importantly, since we're going to talk about catalysts, is there some sort of link between equilibrium and kinetics? So, is there a bridge between the two? And we said earlier, well, no, not really. There isn't a bridge, but there is. There is. And we're going to talk about that now. Okay. So, keep in mind that if we have a chemical reaction, okay, Uh, let me do it this way. Let's say you have a chemical reaction and it's one step. Okay, so here's your reaction. Let's say you have reactants A and B, and they're in equilibrium with products C and D. Okay, so this is your forward reaction. We could also write the reverse reaction. Reactants C and D are in equilibrium with products A and B. Okay, so I'm going to write forward for one and the reverse for the other, so that way we keep this straight. Now, if I was to write a rate law for the forward reaction, okay, this would be equal to the rate constant for the forward reaction times the concentration of A times the concentration of B. Okay, I could also write a rate law for the reverse reaction. Okay, so the rate law of the reverse reaction would be equal to the rate constant for the reverse reaction times the concentration of C times the concentration of D. Okay, now one of the things that we said at the very beginning when we looked at equilibrium, okay, at equilibrium, we know that the rate constant of the forward reaction has to be equal to the rate constant of the reverse reaction. So that being said, we could set these rate laws equal to each other. So the rate constant of the forward reaction times the concentration of A times the concentration of B has to be equal to the rate constant of the reverse reaction times the concentration of C times the concentration of D. Okay, so now what we want to do is get all the concentrations together and all the rate constants together. So to make this happen, I'm going to divide the left-hand side by the concentration of A times the concentration of B. So we're going to put the concentrations together. Okay. Okay. All right. So by doing that, we get this: Kf is equal to Kr times concentration of C times the concentration of D divided by the concentration of A times the concentration of B. Now, if I divide both sides by Kr, the rate constant of the reverse reaction, we get that the rate constant of the forward reaction divided by the rate constant of the reverse reaction, this is equal to the concentration of C times the concentration of D. So the concentration of the products divided by the concentration of the reactants, which by definition, that's equilibrium. So equilibrium is equal to, if we take the rate constant of the forward reaction, divide that by the rate constant of the reverse reaction, that also gives us the equilibrium. That also gives us the equilibrium constant value. Okay, so there was an assumption that we used to make this derivation, that we said that each reaction is an elementary step. Or in other words, each reaction is one, or each reaction has only one step. So that way, the elementary step is really the entire reaction. All right. Now, what equation is used to show why Kc is a function of temperature? It's the Arrhenius equation, because the rate constant of the forward reaction is going to be equal to A, the collision constant, times E raised to the negative E sub A over RT. And so here you have the rate constant of the forward reaction, and you've got temperature part of that equation. Finally, let's take a look at this graph. So this is another reaction coordinate diagram showing an uncatalyzed reaction in blue and a catalyzed reaction in pink. And so we have an activation energy that's without the catalyst. You have an activation energy with the catalyst. Okay, so what can we conclude from this graph, from these pictures? Catalysts speed up the chemical reaction by lowering the activation energy. So catalysts speed up the reaction by lowering the activation energy. Okay. And so catalysts are speeding up the reaction by lowering the activation energy, and it's not by changing pressure or volume or concentration. Okay. So catalysts speed up the reaction by lowering the activation energy, and it's doing so without changing the pressure, volume, or the concentration. It does this by providing a shorter energy path. Okay. Which means there's no change in the products or the reactants. It does change the activation energy in both directions. And it gets to the same equilibrium, but only faster. Okay, so it's not going to change the equal. At the end of the day, catalysts just aid the reaction in getting to the equilibrium faster. That's it. It doesn't do anything else except what we've talked about so far.